Thank Derek. Can I start?
Yes.
Okay. Um, Good afternoon, everyone. My name is Chen Jin from IBM Ottawa. Today, I'm going to talk about FFI in OpenJ9, which is a key part of the Project Panama we have been working on over the last couple of years. So this is the first session on this talk. In the next session, I'm going to explain in more details about what happens under the hood in terms of underlying implementation. To get you a better understanding of what happens in this project, I will start some background of FFI and native memory access, the existing solution in Java, and what's the problem with this approach. After that, I'll get back to introduce this project, focus on the overview of this project, and the basic concepts comply with a couple of examples to demonstrate how it works from a user perspective. FFI, Foreign Function Interface, is a widespread terminology describing a mechanism of how one programming language interoperates with another language. In general case, it means to invoke the native code from the dynamic linked libraries written by the C++ code. So FFI provides a way of leveraging the native libraries from the high-level languages. Why FFI is so popular? Because there are tons of valuable native libraries out there come from different areas, like scientific or mathematical related calculations, GPU, graphic database, or network I/O specific operations, AI or machine learning or deep learning specific frameworks, and many other libraries doing some fancy stuff. So there's no wonder that there's a bunch of high-level languages supporting FFI, such as Fortran, Golang, Rust, and many dynamic languages like Perl, Python, Ruby, etc. When it comes to Java, it refers to JNI, Java Native Interface. I believe many Java developers are quite familiar with JNI because it has been out there over 20 years and has been used everywhere to support native implementation. JNI is an underlying implementation of FFI in Java, and it's a first generation of FM framework for the JVM to interact with the native libraries. And it's supporting the callback to JVM from native functions to call the Java method or access the heap data. Let's take a quick look at an example of JNI, because there's something I like to highlight in the code. This is a pretty much simple example from Java to native, which includes 2 steps before the native invocation. The first step is to generate the JNI-based native headers with a Java compiler. The second step is to specify the JNI paths from JDK to generate the shared libraries with the native code. In terms of the naming convention in native, you must follow the JNI rules and protocols. So the red one is a native wrapper, which is mandatory for each native functions. And it will be verified against the native header in JVM to do the safe type check. So whatever the native does, you have to be very careful in writing the native wrappers because it's easy to get things messed up if there are any mistakes in native, especially in case of the tons of the native functions. So the problem with JNI comes from different aspects. First off, it requires Java developers to write native wrappers from scratch for each native functions, which becomes challenging because it requires developers to grasp the C or C+ knowledge to write a native code, which they don't really want to do so. And it becomes a burden if you are dealing with huge libraries with tons of native wrappers in there to be written in order to build the native libraries on each platform you like to run your applications. So it has to be this way, but it's definitely not cost effective from a maintenance perspective. And it becomes tough and complicated when there's a bunch of periodic updates in the native code. So the best way to do so is to decouple the Java developers from writing a native wrapper code. That means the Java developers should be focusing on their own application logic and don't have to get involved in the specifics of the underlying native code. So they just simply treat the native libraries as a black box to call the native to finish up their jobs. The second issue is that there is no easy way to directly exchange the aggregate data between a Java object and native structures, because there's no direct mapping from native type to a Java type. So you have to rely on other workarounds like splitting the native to primitive or non-primitive by leveraging the unsafe or by buffer APIs to allocate the structured memory, which might lead to the blocks because the missing type information in there. And you have to stop the GC gap connection from updating the Java object when interacting with the native structures. Otherwise, it definitely screws up everything. Performance-wise, JVM is not good because the frequent transition from Java to native through the wrapper code is slow, and things getting worse when it comes to a bunch of JVM callbacks because there's no way to optimize the code from JIT. To address this problem, people come up with a couple of solutions. Typical ones like Java native access or Java native runtime. So which are naturally built on the top of JVM, and by leveraging the reflection of the generation code to kind of map the Java object to native structures. In this way, a developer must rely on the external facilities to approach this problem within Java instead of dealing with that from totally inside. And the reality is there's third-party projects are no longer active in the community, which means you likely lose the sustainable support or any enhancement from the community if you're keeping using them in your applications. In terms of the native memory access, Java basically provides two ways to do that: the byte buffer and unsafe APIs. Byte buffer is a lightweight solution to allocate native memories whose lifetime is controlled by the gap caching finalizer. The problem with the byte buffer is that it has a 2 gigabytes limitations in size. There's something restricted by the underlying index scheme. For the unsafe API, most Java developers love to use that because it allows developers to manipulate the native memories in an extremely efficient way. This is supported by the JVM intrinsics and JIT optimization. But this is not a safe programming model because it's easy to make mistakes to crash in JVM. So you are not encouraged to use that and should avoid doing that as much as you can because these APIs are restricted. Let me quick wrap up the challenges we encountered for the native access in JVM. For native invocations, we're able to invoke native functions with JNI, but they come with complicated native wrappers, unpleasant mapping for the native structures, plus performance concerns on the JVM transitions. For the memory access, we rely on a buffer and on safe APIs to do the job, but we need a more efficient and safer mechanism to unify the memory allocations. So the perfect solution should integrate everything necessary to streamline the native access in Java without any restrictions. That's why we have the project Panama. Project Panama is an OpenJ9 project that promotes the user experience by improving the interoperability between Java and other languages native, especially with the C or C+ code. So the goals of this project are quite straightforward and understandable to users. Obviously, the top priority is fundamentally replace the JNI with pure Java APIs without even sacrifice the performance as compared to the JNI on the safe APIs. With this, JIT will be able to optimize the code everywhere at Java level. So it becomes easier to extend the support to any platform because everything with the native access is done with Java code, and you don't have to worry about the native code because the underlying specifics is hidden from users. The project intends to unify the operations on the primitive and the structured data in native without any limitations in size. And the memory allocation is well managed and automated to ensure it works well in terms of the multi-threading. Apart from that, user will be reminded of the warning by default when they're dealing with any restricted APIs like dereference, the pointer-related memories. So the goal covers every aspect we're concerned about when struggling with the JVM or unsafe APIs in native access. Naturally, the biggest part of this project is foreign function memory APIs, which include the foreign linkers and foreign memory access. The foreign linker APIs enable the invocation between the Java and native, which is something equivalent to the JVM. And the foreign memory APIs is a chart of the heap, the native memory, which the memories in which the memory is described by the layout. There's a tool, FFI specific tools called JExtract, which is used to generate the mesh handler binding code from native headers. So FM API is a second generation of FM framework to support native access in Java. One of the most important features is it comes with a pure Java APIs, which means developers are able to invoke the native functions without any rules and protocols because there's no restriction at all for the native. So this is the part of the biggest achievement in this project. From the roadmap of the jobs, you can see how they're involved in enable the FM support. Initially, the foreign memory access was developed ahead of the foreign linkers, but the first challenge of this project was to solve the problem with unlimited secure access to the native memory. Eventually, these two separate APIs were merged into one JAPS since Java 17, and they kept evolving from there all the way down to the end. So everything with the FM API has been finalized in Java 22. The ultimate goal of the FM framework is to offer a better user experience and comparable performance over the JVM and the safe APIs in order to replace them all. So my expectation that the JVM and safe APIs will be deprecated by default in the future once the whole FM APIs plus extra features become stable and mature in most applications. Let me summarize what benefits we got from the FM APIs. The FM-based applications are easy to write and maintain because they are totally Java code, and there's no rules, protocols, or restriction for the native code. So Java developers are allowed to do whatever they can do to guarantee the code satisfies their needs without any concerns on the native. To accelerate the development, the JExtract tools save the developers quite a lot of time and efforts writing Java code by eliminating the efforts on the mesh handler generations. With the tool, it becomes easy to leverage the existing native libraries because there's so many libraries available for your applications without any modification in native functions. So my understanding is that this is one of the biggest advantages of this project that helps the developer facilitate the application deployment and maintenance when it comes to the native libraries creation. Let's look at what FFA API does. So the intention of FFA API is to offer a safer, efficient mechanism for the memory access, including hypermemory and native memories. So they must be easy for users to take advantage as compared to the buffer, by buffer and unsafe APIs. It comes to a couple of key features to enable the memory access. So the 4 aspects being addressed by these features, which include how to control the memory, how to module the memory, how to describe the native structure in memory, and how to access the memory. One of the most important features is Arena, which takes responsible for the native memory allocation. It has a scope that controls the lifetime of native memory. So the arena provides a flexible way to native management, which is supported by the try with resource block. If you like to allocate memory based on your own policies, the APIs offer something like to customize the memory allocator from arena for your special requirements. In terms of the memory segment, it's kind of an abstraction of the memory which represents a continuous region. So it has a spatial bound and temporal bound, which means if the segment is allocated by arena, it can be accessed only when the arena is alive, and there is no way to access that after the arena is closed. If the segment is allocated by a confined arena, which owned by the single thread, the segment cannot be shared by the other thread. So if the arena is a global or the shared one, that means the arena doesn't belong to any thread. So the underlying segments can be shared by multiple threads. These arena-based rules for segment guarantee there's no unsafe or unexpected behaviors on the memory access. The layout defines the underlying structure of the memory region, which is mainly composed by the two types of layouts: the value layouts for the primitive and the group layouts for the structures, which can be further categorized to different layouts to represent a specific native type, like struct, union, and pointer, etc. With this layout, you are able to create whatever you can do in your application to combine these layouts to describe the native structures. For the memory access, there's so many ways to do that by leveraging the combination of method handler and var handle, which are literally internally supported by the existing APIs and also by the FFIPart APIs. Literally, they are pretty much the same way what you can do with method handler and var handle, like mapping, filtering, and permutation, and binding, etc. To explain these operations, let me take a look at an example to see how it works to access the memory. The native structure on the right side is a point array with two coordinated elements. And the memory layouts on the right side describes the internal structure of the array in Java. With the arena, you can simply allocate the segments for the pointer array based on their size, and create a handle for each coordinator by specifying the name with the pass element APIs. Naturally, there are two ways to access the structure with the var handle. One way is to directly access by specifying the array index on offset, but you probably have to calculate the offset of the elements in the struct. Another way is to call the layouts offsets related APIs to get offset elements and to leverage the method handle combinators to generate the var handle for the coordinator at a specific offset. So you don't have to calculate the offset, but just call the related APIs to get jobs done. This example doesn't cover everything you need to do for your applications, but it does include the key operations on the native memory access. Let's look at what it looks like in foreign linkers. Foreign linkers is something that leveraging the existing method handling facilities in Java to access the native functions, which is kind of a bridge connecting the Java space to the native. So the mechanism is to enable the native invocation is supported by the three artifacts. The first and the most important one is a linker, which contains the key information for the application binary interface specific to a game platform. So like the calling convention and representation of the data type, etc. The linker labels include a downcall and upcall and the corresponding linker options. The downcall enables the invocation from Java to native by modulating the native as a method handler, which is a fundamental part of the linker. The opcode triggers execution of Java method within native functions. So it converts the method handler for the opcode method to a memory segment, which is literally a native address to be evoked in JVM. The linker options actually are extra parameters for the downcode opcode to add some restriction to the native invocation. Things like the return code you like to know, or short-lived critical downcode in the application. These sort of things. Symbol lookup provides a way to get address of functions of global variables in native libraries. What it does is to module the address as a zero-size segment to be reinterpreted in your code. So there are three types of symbol lookup: the loader lookup, the library lookup, and the default lookup. The loader lookup is supported by the caller class loader. In which case, the class loader, if the class loader is removed by the capture connection, and the symbol segments will be released altogether. The library lookup provides another options to get a function symbol as long as you know the library path. For the default library, for default lookup, actually it just simply returns the specific function symbol from standard C libraries on a given platform. So whatever it does, the whole lifetime of the symbol segment is totally controlled by the arena. That means the segment is automatically released once the arena is closed. The function descriptor describes the signature of foreign functions, which is composed by a couple of layouts for the arguments and return type. The descriptor is just used to create the method handler for the downcode and upcode. Let's look at a couple of examples in downcode to see how it works with FM APIs. This is an example for the primitive in downcode. It may not be too much special in terms of the steps to generate a library for the native invocation as compared to JNI. But the fundamental difference comes from the Java and native code themselves. The first thing to settle down in Java is where to put your code for native access. Actually, I already explained it in the previous slides. So FM introduced a mechanism, something like the resource management automation. What happens is there's every single resource in the try block is registered as something to be released by the OpenJDK, in which case the cleanup action will be triggered automatically to free all the related memory once the try block is terminated. So back to the example, the memory related code has to be in a try block of arena, which literally in charge of the life cycle of the memory resources for the native access. That means if there's any memory allocated by the arena, it will be released automatically before leaving the try block. And there's no way to access them after the block. So this is a quite important different from the JNI because it helps to avoid unexpected memory leaks during the native access. Another thing I want to emphasize is the native address is also allocated as a native segment to make sure it can be invoked in the JVM. So the downcode is enabled by generating a method handler binding with the native, which is the key to the native invocation because everything there is totaled based on the OpenJDK method handle. And you can see there's nothing special in native as compared to the generic C or C+ code because there's no rules, no restriction, and no wrapper codes for the native. So you don't have to specify any library paths to generate the shared libraries because everything is the same as what they always do in the normal native functions. This is another example for struct in downcode. As compared to the primitive, the biggest difference is how to allocate and access the struct memory. In terms of memory allocation, you don't have to worry about the primitive because it just passed by a value. So generally, there's no need to allocate memory for them. But things different when it comes to a struct, because you have to make sure the struct can be accessed correctly by the specifying the offset or with the white handle. Because the structured address must be a real address to point to a native memory. The last thing I want to mention is that you need to specify the allocator for the return struct if they have the return struct. So because it needs to because the returned data needs to be a place to hold the returned struct on return. Okay, well, that's everything I have for the today's session. Back to Darren. Any questions?
Thanks, Cheng. Any questions for Cheng? What are you going to cover in your second part of this series?
Basically, we still have a couple example about how to use the JX structure, how it looks like in terms of opcode, and probably we need to more details spend on the underlying implementation in OpenJDK, in OpenJDK and OpenJ9. That's what we're going to talk in the next session.
Okay.
Has very much of the JCL been changed at this point to start using some of these facilities more directly, or is that to come in later?
For our part, I don't think there's too much changes in OpenJDK. I mean JCL in terms of JCL, but in OpenJ9 we do have a lot of changes in terms of the JCL.
Okay, so there are actually examples of the foreign function APIs being used in OpenJ9.
We definitely that's what happens in our case. That's what happens in the implementation. So we have to use that because it integrates in OpenJ9 and in OpenJ9 and OpenJDK. We have to call the APIs from OpenJ9 to make sure it works in OpenJDK. They have sometimes to integrate everything in OpenJ9 and OpenJDK to make it work.
Okay, I guess I'm not sure you're answering the question that I'm asking, so I'll try asking one more time and see. So in the JCL, there's a whole bunch of use of like JNI in various places. Is there very much of that code that's being modified to start using the foreign function APIs?
I don't think so far. Yes, sorry, I misunderstood your question before. So so far, I don't think that there's any further modification in OpenJDK in terms of JCL.
Okay.
So you try to invalidate the whole changes and be after everything is stable in a framework. So
Right.
they just provide an external user for users, not from inside so far.
Okay. And do we have any plans to modify any of our JNI use to start using this in future, like from Java 22 on, I guess?
I hope so. I hope if everything goes fine. Yeah.
Okay, cool.
So with the support for Project Panama versus OpenJDK, and this might be a stupid question, are the use case support exactly the same? I know the implementation might be different for OpenJ9, but are the use cases that are presented to the user the exact same, or are they different in any way? I might have missed that point.
The example is just from user perspective. So what you can see here.
Yeah, from a user perspective, yes. Yeah.
Yes, they should be the same way.
Same, the exact same. Okay, thank you.
Yeah. Just you just
Yeah.
try to show up a couple of examples to make sure you understand what happens out there.
Okay, thank you.
Other questions for Cheng?
Were there any special challenges for the various platforms that we care about versus the platforms that Oracle cares primarily about? Like when we went to AIX and we went to ZOS, did we find any issues with the APIs as they were defined?
From APS business perspective, I don't think there are any difference, but we do do some platform specific details, like little Indian, big Indian issues in our changes, in our implementations. So that's why we had to handle.
Another difference for AIX was unusual alignment rules for doubles.
Yeah, something like that. That's what happens in the structure.
Yeah, I'd assume that the layouts are probably unique across the different platforms for that sort of thing, part of the APIs.
If the user aware of that, if not, they have to be careful to manage the Java code and native code to make sure everything is correct in the layout.
Okay, but as far as we know, we didn't run into any cases of things that like native constructs on any platforms that we wouldn't be able to just naturally call via these APIs, like the way that they're designed.
We'll have code. We'll have a test case out there to make sure it works. Yeah.
Cool.
Thank you.
Once this is complete, how aggressive do you think OpenJDK will be to deprecate JNI?
They have been discussing in the mail list, but so far there's no further follow-up, as far as I know, because I think they're so far still handling some leftover issues. They probably have a couple of jobs coming to integrate with other jobs.
It's mostly for one direction via JNI, right? Like it's for calling out and for manipulating native data structures from Java, but not the other kind of directions so much. Or did I misunderstand that?
We cover Jungle app code. If that's what you mean.
So if I have native code that's making calls into the Java space,
you'll have to go back.
needs to access, Java objects. That's not what this is aimed at, right? It's writing Java code that can access native things, but not for native code that needs to access Java objects.
We just did not mention that in details in this session. It's take too much time to explain it.
Okay, so there's
potential okay, go ahead.
Go ahead.
I was just going to confirm. So there is a part of the API that's designed for native code to access Java.
You can see that. Literally, yes. Upcall.
That's the upcall work that Julian will be talking about next time.
Yes, exactly.
Okay. All right. I'll hold back.
The other potential difference here is OpenJ9 implementation the down call depend on libFFI. And the question is, OpenJDK depend on libFFI as well or not?
OpenJDK don't rely on libFFI to do the job. They have a special implementation underneath.
Yeah, for x86 and AR64, they have a internal implementation. There is work on the zero assembly versions to use libFFI so that they can easily port to other platforms like PowerPC and RISC-V in the future.
Yeah, that's part of their solution for the fallback.
Yeah.
Yeah, I heard the SAP team is going to do they are going to get rid of the dependency on libFFI for AIX and PPC. 64 LE. That's what I heard from them.
That's good to know.
Just a comment before we move on. You talked about access to the heap from native code. That's not necessarily via an upcall. A slice of an array can be passed as, the address of that slice of an array can get passed to native code in a down call. And then the native code can use that like it normally would, just an int star or, parameter.
Yeah. This is okay. This is the generic induction, not too much details about speed to native heap. So I'm not covering this in this session. Any other questions? No hands up.
Last call for questions. Okay, well, if there are none, then thank you, Chang, for the first part here, and we look forward to the follow-on part in 3 weeks.
Okay. Thank you. Thank you for attendance.
Thanks, Jane.
Bye.